Hi there. Welcome back to Core C++ Part 8. I'm Stephan Lavavej, Visual C++ Libraries developer, and today I have a few topics I'd like to go over that have come up from time to time on internal mailing lists I've seen and with external customers. I'd like to talk about the do-while loop, which actually came up with respect to a VC blog post that went up a few days ago. Then on to casts, which are a source of much concern and misery in both C and C++. Then I'd like to talk about the one definition rule, which is a source of terror to those who understand it. And if you don't understand it, you should be terrified. And then finally, if we have time, I had shown my variadic template array sorter back in Part 6. And now that I have time, I'd like to go through that and show you what I was doing there, sort of as a clever exercise. So first, the sort of smallest topic. C++ it's got while loops, it's got for loops. It is go-tos for people who are evil. And there's also this do-while loop, which people occasionally use. I'm not fond of it. I actually forget where I learned this. I'm probably quoting one of my C++ books verbatim. But the do-while loop, I believe, should be avoided almost all of the time. And the reason why, imagine you write something, any loop in C++. Say you do something like, a while. Say you're processing a vector or a set, and you're like, okay, as long as the set is not empty, then I'd like to go, process some elements in it, or as long as some count is greater than 0, or whatever. So in the body of your loop, you have what's known as an invariant, something that's got to be true in order for the loop to actually work without crashing. For example, in this case, the set has to be non-empty before you, say, look at the first element and then go do something with it. Or the count has to be greater than 0 before you go do something with whatever you're counting. If the invariant of the loop is violated, that means that you could be doing work when you're not supposed to be doing work, or you could be dereferencing some pointer that's bogus, or going off the bounds of whatever, or trying to access an element of a container that's empty, things like that. So the invariant of your loop has to hold. So people who are experienced programmers, they pay attention to their loop invariants when they construct a while loop, or in a more structured for loop where you actually specify a starting condition, and then a termination condition, and then how to proceed to the next iteration. If you have a do-while loop, though, things are strange. Because when you say do stuff, and then you say while condition, like this, it's even strange for me to scribble out. What happens is that the body of the loop, the stuff here, it's executed unconditionally the first time around. You always go and do the stuff until you hit the end, and then the condition is evaluated. And if that's true, then you'll go do it again and again. So the condition is being evaluated at the end of each cycle of the loop rather than the beginning, as in, say, a for loop or a while loop. So this is strange. Sometimes people use it, but I'm convinced that whenever you're tempted to write a do-while loop, you should try and think really, really hard if you can possibly avoid it. Because when you execute the body of this loop, either the actual loop invariant condition or something very close to it has got to hold in order for that body to actually be valid and do anything. So really think about what you're doing the next time you're tempted to write a do-while loop. I can think of one exception. Maybe you can think of more. But this is the only one that readily comes to my mind, where a do-while loop is not only convenient, but it almost seems necessary, and trying to avoid it would be very obnoxious. So the example I can think of is in the standard library. Here I've got a vector. I push back 11, 22, 33. I'm using VC11, I guess, update 1, so I don't have initializer lists in Milan. And then imagine that I want to cycle through every permutation of this vector, which contains 3 elements. There's an algorithm for this in the STL's algorithm header from C++ 98, and it's called next permutation. So I can print out each element of the loop. This is just a fancy range-based for loop, but it's just printing out each element separated by spaces. And I say, do this printing of the vector while next permutation of vbegin vend. And if I execute this, I actually get first 11, 22, 33 printed, and then I cycle through all possible permutations until I hit the reverse 33, 22, 11, and then I terminate. The reason why a do-while loop works here and actually seems natural here is purely because of how next permutation is specified. If we look at how this works, let's see, I believe it is in sorting. Yes, permutation generators. There's this next permutation algorithm that takes iterators, returns a bool, and it's the nature of the bool that it returns that's interesting. It says, it takes the sequence, transforms it into the next permutation, blah, 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 lexicographically sorted. If it can get to another permutation, it returns true. However, if it has gotten to the end, and then you try to get the next permutation, it returns false and transforms it into the smallest one, which is ascendingly sorted. So if you go back to the loop here, what this means is we unconditionally execute the body of the loop, but that's okay because we always know there's at least one permutation of a sequence. In this case, I'm making sure it's sorted to begin with. So it's okay to execute this loop unconditionally. Then I say, okay, call next permutation. That will tell me whether it got a new permutation or not. If it did, for example, if it created 113322, then it returns true and I can go execute it again. However, if it found, oh, we were already at 332211, you asked for a next permutation, there isn't one, I'm done, it'll transform it back into 112233 and return false, and then we exit the loop. So the semantics of next permutation basically exactly mirror the way that a do-while loop is specified. This is the one case in which I'm willing and actually eager to use do-while loop. In every other case, I really try to avoid it. So the next time you're tempted to write one, think about that. Okay, so that was a very small topic. On to casts, which is completely unrelated. So casts, people write them all the time, and sometimes, I want to open up the standard. Sometimes I'm convinced that they're not really thinking about what they're trying to say. I'm always big on the C++ language is a way for programmers to express themselves to the machine and to other programmers. And you should always be trying to think, what am I saying when I write a program? If you just write stuff to try to make the compiler shut up and compile and hopefully do something that looks reasonable, that's not good craftsmanship. So when it comes to casts, they're very dangerous because they're an excellent way to make stuff compile, but they're also an excellent way to shoot yourself in the foot, as the proverb goes. So I'm going to leave C casts aside for the moment. One of the confusing things about casts is that there's so many of them. There's 4 C++ casts. You got your static cast, your const cast, your reinterpret cast, and then your dynamic cast. And people who have not played around with all of them extensively are often sort of confused. Which one do I go for? So here's just sort of my quick overview of the standardies and what you're really saying when you say a cast. So static cast, in some sense, is, well, okay, const cast is the simplest. Yeah, let's do const cast first. So const cast is extremely simple. What it does is it casts away constants. So if you've got something like an int star, okay, int star p to modifiable, and then I have a constant star pointer to const, and then I'm going to go fill them, make them point to stuff. I can implicitly convert from int star to constant star. This is cool. I can say, okay, PC equals PM. I'm taking a pointer to a modifiable int, and then I'm assigning it to pointer to constant. I'm saying, okay, I'm no longer interested in modifying what this points to. So the standard, the way the pointer conversions work, it's in clause 4, say, okay, it's always cool to implicitly convert a pointer that adds constantness, or volatileness, but I'll ignore volatile for the time being. However, the reverse is forbidden. If I try to say, okay, I'm going to say PM equals PC, this will not compile because you're taking a pointer to constant, which you've promised you're not going to write through it, and then you assign it to a pointer to modifiable int, which can be used to go modify through the thing. So this sort of conversion is forbidden from happening implicitly. But if you say const cast, in this case, this should be hopefully pretty familiar. If I say PM equals const cast, it looks like a template, but it's not really a template. It's just a part of the core language. I say const cast to int star of PC. This will now compile because I'm explicitly casting away constants. I'm saying, yeah, this points to a constant. I'm going to cast away the constants and then assign it to pointer to modifiable int, and this alone will compile. Now, it doesn't actually allow you to modify data that's been born const. C and C++ have a rule that if, say, a local variable like a const int x, if it was actually defined as const, then you can get a pointer to it, that would be constant star. You can cast away constness to that pointer, but any attempt to actually modify that object that was born const triggers undefined behavior. Now, conversely, if an object was not born const, then it's okay to store a pointer const int to it and then cast away the constness and then write through it. C++ is ultimately only concerned with the constness on the declaration, on the definition of that variable. People often freak out and they're like, oh no, if you cast away constness, things could be bad. And it is true that if you remove that const protection, it is possible to write bad code, but every once in a while you're faced with an API that takes, say, char star, and it's only reading it, and you have a const char star because you're being a good programmer. In these situations, a const cast is necessary to make it compile and do the right thing because you're working with an API that was not designed correctly. But in general, you know what I say about casts, they conceal something broken. So you should try to avoid even a const cast. Now, for static cast, this one is getting increasingly confusing because it does not simply remove constness. The way I like to think about a static cast is that it reverses an implicit conversion other than constness. So, for example, if I have a pointer to derived, and that's what the standard use here is saying, that will implicitly convert to a pointer to base. Everybody is familiar with such conversions. I can use a static cast to say, okay, I have a pointer to base, and I'm going to guarantee as the programmer, I know what I'm talking about, that this thing really points to a derived. In that case, you can say, okay, static cast to derive star of my base pointer. So you're reversing implicit conversion. You can do this in a whole bunch of other cases. You can take a pointer to void and actually cast it to a pointer to t. That will not happen implicitly, but a static cast will allow you to guarantee that, yeah, this thing really is this type I'm saying. And if it's not, then you get undefined behavior as usual. It can also be used to sort of disambiguate types. And you can think of it as a conversion, but it can also be sort of type disambiguation. Imagine, let's see, let's get an example here. The signature of something like std_min or std_max. So if I've got, std_max, what it takes is, it's a template. It takes const tref, like this. And print semi. And it's a template. Now imagine that I've got, say, a local variable, and say I've got something like long ll equals, whatever, something. And then I've got some other variable. Suppose that it is just a little int I equals, and then I've gotten this from something else. And then at some point in my program, it becomes necessary for me to take the maximum of either ll or I, and then go assign that maybe to ll itself. So I would like to be able to write, okay, say ll equals std_max, I've got some using std up there, of ll and I. Okay, this will not compile. As we saw in template argument deduction, what the compiler is going to do is, for each function argument and function parameter pair, it's going to try to figure out what t is, and at the end, all of the deduced t's have to agree. Otherwise, template argument deduction fails, and the compiler will throw up its hands and say, oh wait, I didn't see any other overloads here, so I don't know what you're trying to do. In this case, here it would deduce t to be long, but in this case, the type of I is int, and it's going to deduce t to be int. And at this point, template argument deduction says, I have no idea what you're trying to do. I'm getting conflicting answers for t. I can't instantiate this overload. But as a programmer, we know what we want the compiler to do. We would like max to be specified in terms of long. So what you should do actually here is use a cast. You may be tempted to use explicit template arguments. Do not do that. That will fail to compile in certain cases for reasons I can go into in the comments if you're extremely curious. I may talk about that later. In this case, a cast is actually a good way to tell the compiler what you want to do here. You can say blah, 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 and then static cast to long of I. Here. So what you're doing is you're saying, okay, I've got this int I. I would like to convert it through a static cast. So I'm being very explicit to the type long long. So this is totally safe. It's a widening conversion, same sign, nothing weird happens. We take the same value and we just say, okay, now this is bigger, it's a long long. And this happens to be the same type as LL. So now template argument reduction succeeds. It says, oh, T must be long long because that's a type here, and you've also casted the type to long long here, so everything agrees. We get a long long out and it's assigned to LL and everything is cool. So static cast can be useful in cases where you would like to explicitly convert types when just preserving the original type would not be necessary or not be desired. In addition to things like saying, okay, I've got a pointer to base. Yes, this thing really is a pointer to derived, and so forth. So you can look at all the standards, but those are the sort of two primary purposes. Oh, and every once in a while, I'll see people, for example, in this case with std max, saying like static cast to long long of 0, or 5 or whatever, some constant. That though, that's kind of pointless because you can always add a suffix to a literal saying like 0LL with capital L's if you want to be nice. That actually has the type long long. You don't need a static cast if it's a literal, but you do if it's a variable. That's why I said int I there. Let's leave aside dynamic cast for a bit because that's sort of the odd one out. Reinterpret cast. This one is the sort of the strangest and the most dangerous one of all. So the way to think about reinterpret cast is it's not like static cast. Static cast says I've got some variable and I want to either perform a conversion that would happen implicitly, but I want to do it explicitly, like say into long long. I want it to happen here, or reversing an implicit conversion. Static cast will do that. Reinterpret cast does something entirely different. It says I've got some bits here. Hey compiler, I would like you to reinterpret them as some other bits. So this can do really, really crazy stuff. It can convert ints to pointers and pointers to ints, just pretending that their bit patterns are something else. And that is often interesting. Now, it's sometimes necessary to use reinterpret casts, but they're often used when they should not be used. For example, it's probably easiest just to scribble this out. Imagine that I've got something, let's see, imagine I've got some base star, P, okay, and I've got, say, some more derived class. I've got, some crazy inheritance hierarchy, multiple branches, multiple levels, and I've got this pointer to base, I can say PB, and I want to convert it to this more derived type. So if I write reinterpret cast so long, remember as you write out this horribly long cast that it's really evil, which is why it's so verbose, to something like more derived star of PB. Okay, this will certainly compile because the point of cast is to make the compiler shut up and do what you're saying. It will often seem to work, but not always. The reason why is this tells the compiler, hey, you've got this pointer to base, and just pretend those exact same bit pattern, some address somewhere, actually points to a more derived. In particular, this assumes that base and more derived exist at the same offset. In the case of multiple inheritance, this is not true. If I've got some horrible hierarchy with like multiple bases, I could say, okay, I've got some more derived, some struct or something, and it's going to derive publicly from some meow class, meow, and then also publicly from some derived class, and maybe say it's just eventually a base, like this. So in this case, if meow stores some data members, the layout of derived, see now we got to talk about layout, this is how horrible it is. You've got your more derived object here, and the meow will be first at offset 0, and then of course this is not guaranteed by the standard, but physically this is what is happening. And then you've got your base object and whatever. So if you have a pointer to more derived, maybe say it exists at address OX, A000 or something like that. If you attempt to reinterpret that as a base, you're saying, okay, there's a base sub-object that lives here. And it actually doesn't. It lives at an offset because you got this extra meow base in there. Reinterpret cast doesn't know any of this. It doesn't care. You gave it some bits, and it's going to say, cool, it's these other bits. I'm done. It's not going to change the bit pattern. So this is extremely dangerous. Basically, you should never, ever use reinterpret cast with inheritance, because it will seem to work and then it will fail to work as soon as somebody introduces an extra base or does other things. Now, in contrast, assuming PB really does point to a more derived, if I didn't say reinterpret cast, but if I said static cast to more derived star, this will compile and it will work properly, because at compile time, the compiler knows the relationship between base and more derived. It knows it because it can always go from more derived star to base star implicitly. So when you say static cast, you're asking the compiler, please reverse this implicit conversion for me to go from base to more derived star. So in physical terms, what this means is that the compiler will apply any necessary offset to adjust the pointer. For example, if this is the layout and you've got a pointer to pointer to base here, then if you try to static cast to a more derived, I may have reversed what I was saying earlier, but the fact that you've got this meow here is what's important. If you've got a pointer to base here and you static cast to more derived star, the compiler knows about this extra meow base in there. So it will adjust your pointer from A00, say F or whatever, back to A000, and you will actually get the correct more derived star. So static cast, it will respect inheritance hierarchies. Reinterpret cast will not. Sometimes you do need to reinterpret cast, like if you've got a pointer to floats or something and you really want to pretend it's just a pointer to unsigned char. In that case, a reinterpret cast can be appropriate, but really be careful when you're about to use one. Dynamic cast, the fourth and final of the C++ casts. This one's special. This is used with inheritance hierarchies. And what it does is it will query whether conversion is possible at runtime using the same machinery for virtual functions, RTTI, that sort of thing. So you can take a pointer to base and try to dynamic cast down and say, okay, is this thing a derived star? If it is, give me that pointer. If not, give me a null pointer. You can also do the same thing with references, but in that case you'll get an exception because there's no such thing as a null reference. So dynamic cast, it's safer in the sense that it can know whether it really points to a derived object. However, you pay a runtime cost because it needs to go query that, whereas static cast will guarantee, you're the programmer and you're saying, I guarantee this thing really is derived. Just do it, apply any offset if necessary, but don't go query the type or whatever. I'm not a big fan of dynamic cast either. I don't like cast in general, but dynamic cast, oftentimes people will use it when they really should just be using virtual functions. If you're trying to write something like, okay, let's try to dynamic cast down to derived 1, say I've got a polygon base class and I'm trying to cast down, dynamic cast down to triangle star and then go do something, or try to cast down to rectangle star, do something. What you're really doing is you're re-implementing virtual functions. You should just have a single virtual function draw or whatever, and then you go invoke it and that will automatically select the right implementation. Sometimes dynamic cast is necessary. It does power some crucial things in the standard library, for example. But if you're tempted to use dynamic cast all over the place, ask yourself, should I be using virtual functions for this? So those are the 4 C++ casts. I said I was leaving C-cast to the end. So let's go look at those. Let's see, that's section 5.4. Okay, so C-casts, they are the worst and most horrible of all casts because they will expand to any of the 3 C++ casts except for dynamic unpredictably. So when I say C-cast, I'm specifically talking about, okay, I've got some thing X, and I say, okay, cast it to a T. So I could say, you know, paren int of X, or, you know, void star, whatever type in parens. We're all familiar with C-cast. Now, in C, things are pretty simple. In C++, because we have these C++ casts that describe things at a very fine grain, the C-cast is actually specified in terms of the C++ casts. And here's the standardies, and this should actually start to scare you. Let me zoom in on this. So the way that a C-cast is specified is it will try to do C++ casts in a certain sequence. And the first one that can actually work, it does. In human terms, in English terms, the C-cast is really desperate to make your code compile. And it will do whatever is necessary almost in order to make it compile. This is scary because although you can figure out by looking at the code closely what a given C-cast will do, you have to look at the whole context. And it can get very desperate. So a C-cast will try to cast away constness, and if so, that's all it will do. But it's also willing to do a static cast, or a static cast plus a const cast, or if there is no way to do a static cast, it will go all the way to just reinterpreting bits. So this means, for example, and I've actually seen this in production code, imagine I've got a pointer to a base, and I say, okay, I'm going to do a C-cast to derive star. This is dangerous. This is exceedingly dangerous because it's going to try to do a const cast. That won't work. Then it's going to try to do a static cast. Now, most of the time this will work if there is in fact a relationship between base and derived. However, suppose that you get it wrong. And you might be saying, okay, I could never get this wrong. Yeah, you can get it wrong. If there is no inheritance relationship between your base and derived, the C-cast will be willing to go all the way to a reinterpret cast and just pretend that these bits are some other bits, and then it'll compile. How could this happen? Well, you could have heavily templated code. And base could be base templated on stuff. Derived could be templated on more stuff. And if you get all of your template stuff slightly incorrect, there could in fact be no inheritance relationship between base and derived. Now that would be a bug. However, it would be nice if it simply failed to compile, so you were informed of the bug. Instead, if a C-cast becomes desperate and goes all the way to reinterpret cast, you will not be informed with a nice compiler error. Instead, things will simply compile and then crash at runtime. I have seen this in production code in the STL. It is bad. Do not use C-cast if you can possibly avoid it, and you can generally always avoid it. Instead, figure out exactly what you want in terms of a C++ cast and actually write that out using the verbose syntax. It is verbose for a reason. The reason is A, to make you think twice, and B, it's actually searchable, greppable. So if I'm looking for all of the casts in my code, searching for a C-cast is terrible. I mean, look at this stuff. It's got parens, maybe it's got a star in there if you're casting to a pointer. You can't really search for this. Searching for parens will give you like all functions and stuff. You could if you've got something that will actually parse it and give it an abstract syntax tree, but that's really high-powered machinery. Whereas if I'm careful about always saying static underscore cast, reinterpret underscore cast, I can search for that very easily in any editor I like. So you should really try to stay away from C-cast if you can possibly avoid it. Now, you may be wondering, oh, well, I don't like writing that, but I can say something like this. I could say int paren x. This is what it's sort of interesting. It's known as a functional style cast. C++ added it a while ago, and it is actually not cool. Here is the standardese over in 5.2.3, and we do need this this sort of notation in order to construct temporary variables from nothing or from multiple arguments. Like if I say, you know, vector int paren blah blah blah, that's going through this notation. But when there's a single argument, look at the standardese here. It's saying if the expression list is a single expression, this functional cast is equivalent to the corresponding cast expression. So what this is saying is, if I write something like int paren x, this is equivalent to the C-cast. It is new style syntax, new meaning in the sense of being added by C++, for the old style C-cast. So they're essentially equivalent. I'm equally distrustful of both of these because A, they're both impossible to search for, and B, they are both willing to go all the way to a reinterpret cast if necessary. So if you've been writing this sort of syntax, thinking that, oh yeah, you know, this is the new style way, no, it is bad. Avoid it. Always use the blah 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 underscore cast if you're going to do casting. So that is cast, which comes up pretty often. Let's see. Okay, so I also wanted to talk about one definition rule in this grab bag of topics. So the ODR, as it is known, is, many people have heard of it. Some people have never heard of it, which is actually kind of terrifying because it is so central to almost all C++ programs because of how header files and source files work and macros. It mixes a whole bunch of things. And the worst part is that when you violate the ODR, typically you do not get any notification that you've done so. Instead, stuff just bizarrely stops working. I have actually spent what seems like years untangling ODR issues. So the ODR, what it is saying is, when you compile, here, let me sketch this out, because often people don't even really think about the structure of a program. What you've got is you've got a bunch of translation units. I'm going to say TU here. This is the way the C++ standard sees the world. And these all go into a single program. Okay. So you end up with, I'm just going to say executable at the end. I'm going to ignore like DLLs and stuff here, but they're basically equivalent. The way that it really works when you compile is your translation units become object files. So this is compiling. Then your object files get linked together. Okay, this is cool. Okay, so the standard is translation unit. What this means is you can think of it as a source file plus all of its headers included recursively. It is the thing that is given to the compiler after pre-processing. So translation unit is really a CPP plus any headers, so HPP or .h or whatever extension you're fond of. All of these get included, I guess I can draw that arrow the other way around, to make a translation unit, then it gets compiled into an object file. So what the one definition rule is saying is, imagine I've got some function, void foo, that's defined in some translation unit. Now, it would be very strange if C++ allowed you to have multiple definitions of foo's implementation. So I've got one CPP file in here. I say, okay, void foo, paren, and then I'm going to go do stuff. And in some other translation, I say the exact same thing. So the compiler is required, sorry, the implementation, when the standard says implementation, it's referring to compilers and linkers together, considered as a unit. There's this whole convention that it uses. The implementation is not required to handle multiple definitions of foo. And there's varying levels of the ODR. It first begins by saying no translation unit shall contain more than one definition of any variable, function, or class, or whatever. So the way the core language standardese works, this is one of the things that can be confusing if you've never read it before. When it specifies something using the wording shall, that means that if that sentence or paragraph or whatever is violated, the compiler or linker is required to issue a diagnostic, a guaranteed error. So because this says no translation unit shall contain more than one definition of a function, if you violate that by having just a single source file where I say void foo paren, and then void foo paren, so I'm not trying to overload it, I'm just trying to have two definitions of the same function, that violates 32/1, and you get a guaranteed compiler error. So that's nice, because the compiler can see that you're trying to define this function more than once, and it can just reject it. Then there's more levels. So if you look through the rest of the ODR, and it's pretty complicated, so I'm just going to sort of scroll quickly through here. Then here, if you've got paragraph 4, it says every program shall contain exactly one definition of every non-inline function or variable that is ODR used, basically present, in that program, no diagnostic required. So in English terms, what this is saying is, okay, you get a guaranteed, absolutely guaranteed compiler error if you try to define a function twice in a single translation unit. That's just bogus. We're not required to accept that, and you'll get an error. However, if you have two translation units, let me put over here, say I've got TU number 2 over here, and this says void foo as well, like this, and TU1 also said void foo. Okay, this is violating 32/4 because your program, your final executable, or DLL, although the standard does not recognize the existence of DLLs yet, you have multiple definitions for your foo taking 0 arguments. And it's not an inline function at all. So you violated that, and because the standard said shall here, ordinarily that would mean compiler error required or linker error required. But in the same breath, it also said no diagnostic required. This is the part that makes the ODR fun, because when the standard says no diagnostic required, what that means is that you, the programmer, have to follow that rule. If you violate that rule, the compiler and linker do not have to complain about it to you. They are allowed by the standard to accept whatever horrible garbage you wrote and then emit something that does whatever. It could work perfectly, it could crash, it could misbehave 2 years later, or the compiler could actually diagnose it and emit an error. You are given no guarantees. It's undefined behavior. So this is saying if you actually have multiple definitions of foo and multiple TUs, you don't get a guaranteed diagnostic. Now in practice you do. Because linkers can very, very easily see, oh, I've got an object file with a void foo here, object file with a void foo here. I do not want to accept that because these are not inline functions. So the linker will give you a multiple definitions found, just as if you tried to call something that's not there, it would give you an unresolved external. So this is not yet the scary part of the ODR. The scary part is what happens when you have multiple definitions of something and the compiler is required to accept it. So step back for a moment. Think about the structure of programs where you've got all these header files and source files. Let me re-scribble this. Okay. People often vary down on the whole header file, source file structure. And yeah, you know, if we get modules in C++, they'll be nice for, you know, compilation time. But I personally do not consider header files to be some sort of abomination. They're actually quite elegant for what they do. So if I've got some header file here, say meow.hpp, and I've got a couple source files, you know, CPP number 1, and then CPP number 2, I could have a single header included into multiple source files. Now, by the way, this is nothing whatsoever to do with include guards. That whole if, and f, and then I need a macro that's very unique to my header, but I'll just say meow. Then define meow. We all have seen this. And then endf at the end, and then you put stuff here. This has nothing whatsoever to do with this other thing. These idempotency guards, idempotency is a fancy term meaning if I do something more than one time, it has the same effect as doing it exactly once, because I should be able to include a header multiple times, either directly or recursively, without anything bad or strange happening. This is necessary so that within a single translation unit, I can include a header and then include a header again through some other chain and not have it expanded twice. It has nothing whatsoever to do with multiple TUs. So if I've got a single meow HPP, although I have put idempotency guards within my meow.hpp, it's still getting included in multiple CPP files, which are translation units that can get linked into the same program. So within a header, and many people, you know, if they've programmed for, you know, more than a couple weeks, they know this rule, but often not very explicitly. It's the ODR at work here. I cannot put a void foo like this within a header, because that'll work if I've got a single source file. The compiler just sees translation units, it sees a single foo, everything's cool. But the moment I include a header file from multiple source files, and I've got a plain old void foo here, I've got multiple definitions of foo. The linker is going to reject that because I violated the nice part of the ODR. So plain functions can't go in headers. Now, what kind of things do need to go in headers? Well, one example is inline functions. If I say inline void blah blah blah, I could say inline here. Okay, the inline keyword, it is a hint only. It's saying, compiler, please consider inlining this. It's not required to obey your hint. It could just not inline it physically, and it won't if you don't have optimizations enabled, obviously. And it can also inline stuff that you haven't requested, so it's just a suggestion. Compilers will often or sometimes ignore it. In practice, VC will consider it, and it will make it slightly more likely to inline whatever you've specified, but it's not a binding, you know, requirement at all. However, if you want inlining at all, the compiler is going to need to have the definition of foo available so it can actually inline it. This is ignoring link time cogen, which is a whole separate thing. That's just optimizer stuff that happens behind the scenes. For traditional inlining within a single TU, at compile time, the definition needs to be available. That means that the bodies of inline functions need to go in headers. But then what about this whole problem where I've got a single header file that's being included in multiple source files? Yeah, inline is a hint, but I need the definition in the header. So I need to change the rules about not having multiple definitions of foo. So what the ODR says is if you have an inline function, you can have more than one definition of it in your whole program. This is what I've often referred to as the partial ODR exemption. You can have more than one definition, but they all have to be the same. Something very similar happens with templates for a different reason. So imagine that I've got a template here, and I say template, P-L-A-T-E, on type name T, void bar, taking, some T, and then I'm going to go do stuff. So when I know what T is, I can stamp out a body of T. However, that body, that implementation of of bar, will depend dramatically on T. If T is manipulating ints, then a simple, T plus U could just be an instruction that adds two integers together. Whereas if T is like a stood string, then I say T plus U, now I need to go emit a function call that calls the concatenation operator for stood string. So the stuff, the object code that the compiler ultimately has to emit for a given call to bar depends crucially on the body of the template. What this means is that when you call bar, if you're using implicit instantiation, which almost all templates do, the definition of bar needs to be available. Now, this is exactly like the case for inline functions, but for a different reason. For inline functions, we need the body if we ever actually do want inlining. For templates, we need the body because stamping out the template, instantiating it, depends on what the template is doing. So the summary of that is templates need to go in headers. And this is something people almost always find through trial and error. They try to put a template in a source file, and it doesn't work when they try to use it from another source file because the compiler doesn't have the body available. So the definitions of template functions, function templates, need to go in headers. But again, this could appear in multiple TUs. So template functions, function templates, I keep saying it in the wrong order, they also receive this partial ODR exemption. So what the standard says is you can have more than one definition of inline functions or function templates in a whole program as long as their definitions are exactly the same. If they are not, you violate the ODR, no diagnostic required, and in practice, the linker will not complain. Stuff will just link and compile, and everything will seem okay until your program misbehaves horribly. This is the real scary part that you really need to obey. And there's these whole conditions about what it means to be equal. Basically, they can't differ except for white space. They allow white space to be different because that's okay. So what this means is that if you put an inline function or a template into a header, then you're okay. Because the definitions that appear in every translation unit that gets compiled will be identical. What the linker will physically do is when it sees all these object files being thrown at it with multiple definitions of your bar template or your inline function foo, it'll pick one, whichever one it likes, and it's going to throw the rest away. In fact, it's referred to as a pick any or select any comdat. In VC's terminology, comdat meaning like common data or something. So what this means is that if your definitions differ, the linker will appear to select one at random almost, and then use that, not using, just completely ignoring these other definitions. So don't allow them to differ. This means don't just define stuff, like if you've got a header, centralize it. Don't just repeat things like templates because you know the body. Don't copy and paste code. Put it in a header. The other thing to respect the ODR is be extremely, extremely careful, and this is another thing that it feels like I've spent years fighting. If I've got a header, suppose I've got my meow HPP, okay, and I've got, my idempotent cigar, so my if and def meow and all that stuff, and then I say something like, okay, if def, or maybe I say if, okay, if def. If def mode X or whatever, then I'm going to say, okay, template on, type name T, blah, 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 void bar, okay, taking a T, and then I'm going to go do things. I'm going to maybe call stuff 1 or stuff X. Okay, stuff X sounds good. Blah, blah, blah. Else, if I'm not in mode X, then I'm also going to have a template bar, because templates need to go in headers. And instead I'm going to go do something else. So, other. I'm going to go call other, and then I'm done. Okay, so exact same, template, blah, 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 I'm just scribbling there. So what I've done is I've put code in a header, whether it's a template function or an inline function or both. and I've made it dependent at preprocessor time on some macro that switches between modes. So this itself, it's not incorrect, but it's extremely dangerous because it's correct if all of the header files and source files that are compiled into a whole binary, a whole exe or DLL, agree on the setting of mode X. In that case, everybody sees either the definition that calls stuff X or the definition that calls other, and everything is happy because all the definitions are the same. However, if you've got multiple translation units that disagree on the setting of mode X, what have you got? You've got one definition of R that calls stuff X and another definition that calls other. This violates the ODR, no diagnostic required. In practice, stuff will just randomly fail to work if you're lucky. Otherwise, it might work and then crash 2 years later. So when you write code in headers, just be extremely careful to not make it depend on macros to switch modes. I like to say modes are evil. There are ways, there's pragmas, we got pragma detect mismatch that can sort of help the linker understand when modes are conflicting, but the best way by far is to avoid violating the one definition rule by making everything consistent. So modes, extremely evil. Okay, so that's basically all I wanted to say about the one definition rule. Looks like I've got a little time. So back in part 6, I had shown my variadic template array sorter. I scrolled extremely quickly through it. It turned out somebody was actually able to transcribe it, but I didn't have time. Well, let's see. I didn't have time to explain what it was actually doing. So let me do that now. Let me just get rid of this so I don't get confused. Okay. So let's go look at this. Here I'm using the Milan build. Actually, this is just from a few weeks ago. So it's very recent, supports variadic templates, all that other stuff. You can also compile this in the CDP, although the CDP has more bugs than what I've currently got here. So what I'm doing, this was motivated by a question that appeared on our internal mailing lists, where somebody said, okay, I've got this static table of data indexed by like IDs or something, and it's got, I can't remember what the value type was, but he wanted to sort it according to the keys in this table. And he wanted to do it at compile time rather than running some script or just validating at runtime that it was really sorted. And because we had just gotten variadic templates, I was like, oh, I can write this. So it's not an especially realistic exercise. I'm certainly not saying this is something you're going to be writing all the time. No, it's not. But just like breaking a board in karate is useless, and yet it kind of uses skills that are used elsewhere. Writing this taught me some things about writing variadic templates, and it's just interesting to see the techniques you can use when doing actual work with variadic templates, like say writing make unique, as I did before. So let me walk through what I did here. So I got this whole thing here in my plain text editor. So I begin with writing this thing. I say template int vals struct ints. This is because I'm going to want to process here. I was restricting myself to integers. I want to sort a bunch of ints. Let me actually show you the usage here. Okay. Eventually what I'm going to do, let me spin up a new copy of this. Come on, it'll click. Why am I not getting a new copy? Here we go. Okay. Delete for some spacing. Okay, so if I want to sort stuff at compile time, I can't just say like a bunch of ints, comma, comma, comma. I need to give them to something. So I can give them as non-type template parameters to a variadic template. So I've got this struct here called sort that's templated on an arbitrary number of ints, and I could say, okay, sort of, and then give it a bunch of ints, and then I can go reach in and extract a nested type. And here, this type will be this ints dot struct. So I could have, here, let me show you, if you've never seen non-type template parameters before, if I said template int vals, this would be templated on a single int. So I could say ints of 5. So that's nice if I only ever need to talk about one int. But if I want to be talking about an arbitrary number of ints, I can package them up by saying int dot dot. Now I can say ints of something like, 11, 22, 0, -9, whatever. And this is a valid type to talk about. It doesn't do anything. That's why it's an empty struct. So this will be the way that I package ints up and then manipulate them later. So that's sort of the first helper that I needed. Then, because I'm eventually going to write a merge sort, I need a way to concatenate two lists of integers together. So that's what this concat helper does. Let me show you what this does. Copy it out to a new editor. Okay, so I've already got my ints there. Let me rewrap this a little nicer. I had written this in a wide editor, but I've reduced my resolution to project here. Okay, so what I've got here is a declaration of a struct, and it's templated on two types. This is not a variadic template. So here, just given this, and I haven't even bothered to give concat an actual definition, but I could talk about the type concat of like double and, I don't know, void star, or whatever, or, you know, many pointers. This is okay because it's templated on two type names. I've given names to them that are suggestive, but this doesn't have any actual requirements. There's no concepts. The reason I've done this is because I then want to partially specialize concat. So I provide a partial specialization of concat for two of these wrapper structs, ints. Ints of vals1 ... and ints of vals2 ... And so this one, if I say concat of ints 1, 1, 2, 2, and then ints of 0 and 55, this will select this partial specialization. If I say anything else, like concat of double and ints of 0, this does not match the partial specialization that we saw in the specializations episode, because no choice of vals1 ... can make ints of vals1 ... equal to double. So this is bogus, this would be bogus. But that's okay, because I don't ever need to say this. I'm only interested in saying concat of a couple ints. And the way to access what those ints are is this whole partial specialization thing. So if I just had an empty struct, that would be nice, but it wouldn't do anything useful. So I've got this nested type here. Within the definition of my partial specialization, I can refer to these what are called parameter packs of vals1 and vals2, and then I can recombine them in interesting ways. So I can say, okay, vals1 ... will expand all those arbitrary vals, vals2 ... will expand those, and then I can glue them together into a single ints wrapper. So usage here looks like if I say concat of ints 11, 22, and then ints of 0, 55. They don't need to be sorted or anything. They could be negative, whatever. Double colon type, this is identical to ints, I could compile this, but this is what it would give me, of 11, 22, 0, 55. So it's a way for me to glue together two lists of integers, but it's done through the mechanism of partial specialization and having a nested type here. So this is just sort of a fundamental technique, I won't say trick, when processing parameter packs. So now I know how to concatenate. So the heavy lifting of a merge sort is done by this bisect helper and then this merge. Yeah, I got the merge helper there. I'm trying to remember what I was doing. Okay, so let's see, bisect helper. Let me copy this. Okay. So what I was doing here, and I'll post this code on my SkyDrive for you to look at. Rather than trying to transcribe it from the video, please don't do that. Okay, so imagine, let's see, here's usage. Okay, so I've got a list of integers. What I want to do is I want to break it up in half. I want to bisect it. Now there was an easy way I could have written this, but I actually chose to write it a hard way. So usage will look like here. Here's the outer struct. Bisect, it's templated on a single type name. And again, I don't even bother providing a definition for this because I'm never going to use the primary template. I only want a partial specialization, bisect for ints of vals. So usage will look like bisect of 11, and then 55, and then 0, and then -9, and whatever. Like this. And then, of course, I'm going to want to reach in and get a nested type. So I've said ints vals ... I'm going to then call a helper. I'm saying call, even though I'm really deriving from it. Everything is happening at compile time, and I'm defining these things recursively. So let me show you what the helper looks like here. Like this. I'm just reformatting it to make it wrap nicely. Okay, so bisect is a wrapper because I need to process things a little before I give it to my helper. Okay, what I do is I start with an empty list of ints, and it's okay if I have a variadic parameter pack to pass nothing. In fact, it's crucial that I can pass 0 things. So I have an empty list here, and then I have all of the ints in the second argument, and then finally I need a third int, a count parameter that tells me when I'm done. Or sorry, this is a bool. Yeah, it's a bool. A bool that tells me when I'm done. So I can use size of ... This is the one time really that the core language sort of has mercy on programmers. Size of ... is not strictly necessary. It's possible to write it using variadic machinery just like this. But because it's often so necessary to get the number of things in a parameter pack, they added this to the core language. If you say size of ... and then a pack, that will be at compile time the number of things in the pack. They just reuse the size of keyword. Even though it's not counting size of bytes, it's counting the number of things in the pack. So I'm done if the number of things in my pack is empty, because if I'm trying to bisect an empty list, then this would say bisect helper ints nothing, and then size of ... nothing equals 0. That's true. So I'd say done for true. So let's look at the base case. This is recursion 101. I've got a base case up here. My bisect helper is templated on 2 type names and then a bool done, partially specializing. If I'm given 2 lists of ints and I've been told that I'm done, then the first part of what I'm bisecting, that'll just be this first parameter, ints vals 1 ... here. And then the second thing, so I've got a second type def, that'll be the second thing. So this is the base case. That's what happens when I'm done. And I've ensured that if I'm empty, I go immediately to done. I don't do anything else. But in general, if I've got more than one thing or more than 0 things, I'm not done. So I use this helper here. And what this does is one by one, it breaks an element off of this second list, which started off with all of the values, and appends it to the first one. So this partial specialization, I need to template it on int ... vals 1, an int x, and then int ... vals 2. And what I'm saying is bisect helper takes this first list that is growing of vals 1 ... and then a second list of ints, the first element being x, and then the second and onward elements being vals 2 ... and this is when I'm not done. And it takes the first element of ints, the second one here, and appends it, and then removes it here. That's what this is doing. When I write this template, I imagine it as a physical process. This is sort of one of my techniques for writing templates. I see ints of x vals 2 ... coming in, I break off that x, remove it, and then I append it here. So this one by one is moving elements from vals here over here. And I started with all of them in the second position, and I'm moving them one by one to the first. And I'm saying, okay, I'm going to be done when the size of vals 1, this first list, plus 1 is greater than or equal to the size of vals 2 ... And I had specified this very carefully to handle edge cases of, okay, what happens if it's odd or even, blah, blah, blah. You can work through it yourself. It's instructive. And the reason why I wrote it like this, there is actually another way, sort of an exercise for the reader. You can write a bisect fairly easily if you're not concerned about stability. You can write a recursive template that takes 2 elements at a time and then feeds one to a growing first list and a second one to a growing second list, and then has conditions for ending on 0, 1, or possibly 2 elements. However, that's not stable, because if I have a list of ints, say I've got, 9 and -5 and 11 and 22 and then 17, 29 and whatever, and I say, okay, this one goes to the first list, 9, this one goes to the second list, -5, this one goes to the first one, and then 22, and then 17, 29. By taking every other element and then breaking that up into first and second, I haven't preserved the original order in some sense. So this could lead to a non-stable merge sort. And I, for whatever reason, even though ints are unique, I wanted to write something that was very general. So I wrote this so that it would preserve the original ordering strictly when bisecting. When I end up here, no matter what order these vals were coming in, it's going to be split as cleanly as possible in half into this first and second list here in the original order. So all of the vals will be there in the original order in first, and then continuing on in second. So this can be generalized to things like pairs or whatever, where I've got some criterion that permits equivalent but different elements. I actually had extended it. It is possible. So that's why I wrote it like this, although if you wanted to be lazy, you could break them off two at a time at the cost of taking every other element. So that's what bisect is doing. Okay, so now let's see merge. This is almost going to do the heavy lifting. Actually, this does the heavy lifting because sort helper is very, very boring. Okay, so how does merge work? Now that we've got as primitives concatenation and bisection, what does merge do? Okay, merge helper. Oh, I only got the merge helper there. I need the whole merge. Oh, that's right. No, I've got merge. Oh, I put merge on the top. Huh. Here we go. Okay, so merge, what it looks like, I've got two lists of integers. This is what happens after I've bisected stuff. And now I want to merge, and I'm assuming that these lists of integers are already sorted. This is how merge sort works. And now I'm going to merge them into a single greater sorted list. So I've got, again, a declaration of a primary template taking a couple type names. These are going to be ints of blah, blah, blah. But the primary template needs to be specified in terms of type names. Then I need partial specializations. I need to handle all the possible cases. So if they're both empty, then, oh, I had to merge nothing. That's cool. I'm done. So my output is empty. If one is empty but not the other, then merging that just returns one of the inputs. And I've specified it in this form to exactly match my partial specialization down here. If you recall, when I talked about specializations, there's rules for figuring out when something is more specialized. By writing it in this form, I'm guaranteed that the correct one will be selected and that I'm not going to get any ambiguities. Even though here I don't need to break off the first element, I just want all of those ints. So this is the case when all the ints are in the second list. And then finally, what happens when I'm given two lists containing one or more? So what this looks like here, because I've already handled the case of both 0, or 1 being 0, 1 or more, 1 being 0, 1 being 1 or more. So here I'm saying, okay, both lists have 1 or more, so I can call them A and B. And then I invoke my merge helper and I tell it, okay, is B less than A? And the reason why I wrote it like this is, again, to handle stability. And then I'm going to give these two to this merge helper, which I've declared. And this is written as take B. And the reason why I wrote it like this is that if they're equal, I would like to prefer the first one. So I only want to take B if B is bigger than, if B is less than A. I want to put that one first. So that's why I wrote it like B less than A. So let's see what merge helper does. Let me reformat this a little. Enter, here we go. Okay, so I need two very similar specializations of merge helper. One is if I've been told not to take B, and the other one is if I have been told to take B. So here we go. This merge helper, this one, let's look at the true case first. This merge helper has been told to take B given these two lists of integers. So what I'm going to do is I am going to merge, recursively call merge, really instantiate, all of the ints from A's list, and then everything but B, because I'm taking B out. And then because I know B is less than A, I want to put that one first. So then I need to concatenate B by itself to this. I had written concat to always take ints, so I need to wrap B in ints even though there's only one of them. And I derive from it, which is how I can get this nested type here. That was just a convenient way. I could say type def, type name, blah, 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 double colon type, but that's horrible. Just deriving publicly from it is more convenient. Conversely, if I've been told not to take B, I want to take A. So I remove A from the list here before merging the remaining lists, and then I take A. So this whole thing actually implements merging. read it through a second time if you got lost on what I was doing there. And actually that's the hard part, because that did the sorting. All of the sort is focused on figuring out whether B is less than A. At this point, it's just a cleanup job. So if I say, let me get this sort here, because I don't want to have to call merge and bisect and all that stuff manually. Let's see, where's my sort here? Okay, so here's my publicly usable sort struct. This is templated in an arbitrary number of vals, and I need to wrap them in my ints wrapper before invoking my sort helper. So that's all I do here. That's all that sort does. What sort helper does is I've got special cases for what if I've been told to sort nothing, okay, I'm done. What if I've been told to sort one thing, okay, I'm done. Otherwise, I've been told to sort multiple things, and I'm saying ints A, B vals. What I'm going to do is I'm going to bisect that list in half. I'm going to break it in half, and I've got helper type defs here. So bisect double colon first, that's the unsorted first chunk of the ints, and then unsorted second is the second chunk. I can then call sort helper recursively to sort that unsorted first and unsorted second. I'm just assuming that I'm going to do the correct thing because I've already handled the cases as 0 and 1. And then, assuming I've got sorted first halves and sorted second halves, I can merge them together. And I know that merge, given sorted inputs, will return a sorted output. And I say type here. That's it. That's my variadic merge sort. So here, what I can do is, if I say sort of, and here I took a bunch of randomly ordered primes, if I reach and grab the nested type, I can print its type ID name, and if I compile and run this, given these totally unsorted primes here, 11, 13, 5, 79, I get a sorted list, 2, 2, 3, 3, 5, indicating that I actually did the right thing. I can even use this, and this is the other mode that my sorter can work in. Let me comment this out. This, and then uncomment this. So it might be all well and good to say, oh yeah, you know, you can take the type ID of this and print it out, but can you actually use that for anything real? And the answer is yes, you can. You can use this to statically initialize an array at compile time and have it be sorted. So all the same machinery as above, except this time I need a helper struct in order to convert this list of ints into something that can initialize an array. So what I'm going to do is I'm going to say sorted array of stuff, and this is going to have a static data member of type std array that will have been statically initialized from all the stuff sorted. And I can iterate through and print it out at runtime, but it was sorted at compile time. The way that works is my sorted array derives from a sorted array helper where I say, okay, whatever that is, sort it, and then give that list of ints here. So sorted array helper is then partially specialized on ints of vals ... and I simply say I have a static const array of int, and how many of them? Well, that's size of ... vals, and then I can write a definition of a static data member of a class template, and what I do here is, let me indent this, I say, okay, sorted array helper ints vals ... When I define the static data member here, I can talk about vals ... So I can initialize it from braces, and I'm putting 2 here because I'm very pedantically correct, from vals ... And this will expand to be 2, 2, 3, 3, whatever. So if I compile and run this instead, let me go back here, and I don't need this anymore. If I compile and run this, I have initialized a std array statically sorted, and then I can just run through it at runtime and then print it out separated by spaces. So you could use this in production code if you wanted to sort a list of identifiers, so you could then quickly binary search through it using std lower bound, or things that are not identifiers. You would just need to customize the sorting criterion. So it's not entirely artificial, although I will admit it's sort of an artificial exercise. Hopefully walking through it taught you something about variadic templates, or just specializations in general. So that's all the time I have for this part. If you have any questions, let me know in the comments. See you next time.